Hello everyone. In this video, I'm going to talk about transform of periodic and power functions. Uh, of course, this type of functions have own applications and and uh, and the work is still kind of similar, but they may involve a little more techniques as you will see. But we do have theorems and formulas and that apply just when you derive or work on these to come up with these transforms, you may get into a lot of different steps. And a review of previous work in algebra does help here, and also trigonometry if you're dealing with trig functions. So let's talk first about uh, we know what the periodic, let's see, periodic function is, let's say, f of t. So this is a definition, a function f of t. We always kind of described it maybe in the first time you've seen it is in trigonometry. You say f of t is periodic. Uh, and has a period, this capital T here. Of course, it can't be zero if the function after that period is the same, right? And we saw that in sine and cosine and stuff, right? So that's you already know when if you look at sine and cosine. So here, let's introduce to a function. You've probably seen it before, the square function, which is the square wave function, can be expressed as f of t, here defined as 1, negative 1, for 1 is between 0 and 1, and negative 1 between 1 and 2. So if you try to get an idea about the graph, of course, you get something like maybe not, it's going to be broken. So here is 0 to 1, and the value is 1. And of course, here's the open because it's strictly greater than 0, strictly less than 1. And then when it comes to between 1 and 2, the value is negative 1. So this can repeat, right? And let's draw it first. And the period here is 2. So since the period is 2, then every other 2, so that's 3, 4, we would expect the same pattern to repeat, right? You have this on top, you have this at the bottom. So after 2, same thing, you have this on top, you have this at the bottom, and it keeps going. So this is the square wave function. It is, of course, convenient to introduce the notation of what we saw before. It is convenient. Um, to introduce the notation that we saw before, which is the window to window the version of the periodic function. You see that we can put that window on it, a window version of periodic function. So we will do that in order to get into these transforms and be able to use it in a better way. Right. So how would that happen? Let's say if you have f sub t, capital T, which is the period of t time, and we can define it there as f of t pi 0 sub 0 comma capital T, which is the period of t. And we've seen this before. It just means f of t times u of t raised to minus 0 minus u of t minus capital T. Right? And that's because of this, we can also, if we want, write it as a piecewise function. We can say with the shift or showing the period here instead of 0 to 1, we can have f of t here, and 0 or t is greater than 0 and less than capital T. And of course here, otherwise it's 0. So the Laplace transform, and I mean, and I will show this in the example. This is just kind of give you what's going on, so when you work in the examples, you know where this thing comes from. So the Laplace transform of this f sub capital T of t is given by, here it is, the capital F we use for the Laplace transform, sub capital T of S is going to be, remember when we did Laplace transform definition at the beginning, it is this integral, right? Kind of like right sided there, 0 to infinity, and we have negative st, and now for using that function here, f sub capital T of t dt, and it can also be using the other notation with the integral from 0 to the period, e negative st f of t dt. So this is it. So this is kind of the formulas, but let's put them together in a theorem and just describe it. So you have a transform of periodic function, and here is a theorem that's going to put this together. If you have a function that has a period, is this capital T, and is piecewise continuous, on closed interval 0 to capital T, then Laplace transform here is given by the two integrals that there, but let's expand on this. And this Laplace transform we're looking for, it's given with this integral from 0 to infinity, exponential to negative st f of t dt, right? And the f subcapital T of s is 0 to infinity, exponential negative st, f subcapital T of t equal, or using from 0 to the period, e negative exponential to negative st times f of t dt. But really, what's going on and what formula you're going to use after this is what they are related with. They are related by this formula that you're going to be using for Laplace transform with sub period here on S is Laplace transform on S times 1 minus exponential to negative S capital T, or really, let's do a different color because this is really the main one. Laplace or the transform f of s equal, so f sub the period of s over 1 minus e to the negative s times the period. So these are the integrals. They are not difficult to prove. There is a proof that is known for these using the previous theorem that we used. But really, what runs into is this is how the two are connected, is using this formula. So let's see an example. So this doesn't look too strange. Let's see an example. Then I'll do a separate video for longer examples, so you get to learn more mechanics if you haven't seen these techniques with math. All right, so determine Laplace transform of function f, where f is the periodic. Okay, so where f is periodic square function. The one I introduced a square wave. I keep forgetting wave function. And the example we saw, the period is 2. So so what I will need to do is window this thing. It is the function, so we can window it, right? And that gives us f sub capital T of t pi 0, 1, or in detail will be pi sub 0, comma 1 of t minus pi sub 1, comma 2 of t. So as you see the picture, here is the for the first one, this thing, then it is for the second one, this thing, right? So we want to figure out that. And we use the previous formula, right? So, which So this is not something to derive. We know how to calculate this window. So the formula is, of course, u of t minus 1. We don't have any multipliers here. Equal minus u of t minus 1. U of t minus 0. This is for the first one. Minus u of t minus 1. Then we do similar thing for this. U of t minus 1 minus u of t minus 2. All right. So now if I want to switch to this FTS, or the capital sub period, I will refer back to this point where we by itself. I will refer back to this formula. So we're doing Laplace transform for this window here. So if we do Laplace transform for the window, of course it's going to be on S. It's nice. So we in a way we have a formula. It's just going to be this. And that's of course with A is less than B and A is positive. Okay, so let's use that for the next step. So if we do Laplace transform for this thing, then we get this here. So now using this formula, it should be for the first one. It's for this one. Now let's use this here. You see the A and B are there, A and B. So it's going to be E minus or exponential to negative S times 0 minus exponential to negative S times 1 all over S. Right. Then now we do the same thing for this. Right. Which this gives us 1 minus exponential to negative S over S minus exponential to negative S minus exponential to negative 2S all over S. And what can we do with this? We have a common denominator, so let's see. 1 minus E exponential to negative S minus exponential to negative S plus exponential to negative 2S all over S. All right, so this is interesting here. Let's combine these like terms and talk about it. Often when we look at this and these exponential forms, we just kind of see them as the way they are. But we also need to see if we can do more to them. So that's what's interesting about this. So to stay in the same page, I'm going to just show you here, like that substitution. If you consider this thing this way, some u as exponential to negative s. So what would e to exponential of negative 2s be, right? The rules of exponents. So we're going to say this is going to become this squared. So it's actually u squared. So if we do that here, it's 1 minus a 2u plus u squared over s, just for now to see what else we can do with this, right? So let's rewrite it. So u squared minus 2u plus 1 over s. And now can it be factored? You see something like that? Yes, it can be factored. And you'll see why we're doing this, because we keep in mind this formula here. We have this here, 1 minus exponential to negative st there. So we try to have something similar to that, and that's the goal. Okay, so what is the factoring for u squared minus 2u plus 1? U squared plus 2u plus 1 minus 2u, right? That's going to be two numbers multiply -1, add two -2. So that's u minus 1 times u minus 1, so which is u minus 1 squared. So I'll take it back to the exponential form. So exponential negative s minus 1 squared, right? I'm trying to keep everything this pace so you see the thinking that you will need to do with keeping in mind this. And keeping in mind this, look, you have 1 minus, not exponential minus. So maybe I can do that here. Can I do, so question, can I do 1 minus exponential negative s? And if I do that, what happens? Usually when you do that, a negative will be out, right? Because when you have 3 minus 2, and you switch to 2 minus 3, they're not going to be the same. You will have a negative out, right? But when you have 5 minus, let's say 2 squared, then you do 2 minus 5 squared, nothing happened. It's the same thing, right? Because it's squared. So here we can say that this is 1 minus exponential to negative s squared, all right? So hopefully you can redo this to see when you look at something and you have something else in mind, how you'll walk your way and adjust so everything works out towards the end. Okay, so now let's keep going. We're finding out this thing. So now I can say it is 1 minus exponential to negative s squared over s. Okay, so now you'll ask, what are we doing in the first place? We're finding Laplace transform for this periodic function. It's always piecewise continuous and all that. And here is the formula. Now that we found this, we need to divide by this two terms here. So f, or capital F, on s, or of s here, which is Laplace transform of the function, of course, of t on s, is going to be what we found divided by 1 minus exponential to negative 2s. Okay, I'll stretch this a little more because it's going to help you with the bigger problems. Also here, you're going to say, is there something I can do? Well, let's see. Here is a suspect. 1 minus exponential negative s all squared. Yeah, okay. If this is again, let's do different. If this is again, I lost even the cost. If this is if we use that idea again, we know that this is 1 minus that, right? So, and we know from different squares that this is y minus 1 minus u and 1 plus u. So I can do this as 1 minus e to negative s and times 1 plus e to the negative s. So you see something that doesn't look can be factored can actually be factored. All right. And I have two of them here. One is out. One is remaining. And that's it. So we did find it. So here is the answer. Laplace transform of this periodic function, which is here the square wave function is 1 minus exponential to negative s over s times 1 minus exponential 1 plus exponential to the negative s. This is pretty much how you do these examples. The only thing that's going to happen um, is you see these tricks with the algebra uh, and and trying to simplify the answers is what you would need to do. Um, uh, let's see. Yeah, we can do one with involving Taylor series. Why not then? And then close this video. So let's say we need to determine Laplace transform of this function, where the function is see where the function is defined as sine of t divided by t when t is not 0 and 1 when t is 0. Okay, so I think here you're gonna say, how do I do this? But you've seen in calculus before that you can express the sine function as Taylor series. Express sine of t as Taylor series, which gives you sine of t. So this is from what you've done in the past. Yeah, and you just recall the formula. All right, so to get f of t, what we need to do, we need to divide by t, right? At least that part there. Um, all right, divide every term by t. T cubed divided by t. T to the fifth divided by t becomes t to the fourth. T to the sixth. All right. So if, for t, of course, it's a positive. This we know that the representation also holds at t equals 0. And we know that when you do limit for this thing here as t approaches 0, the answer is 1, right? Which you can see clearly here, of course, right? When the limit as t approaches 0, the answer will be 1. So can we do Laplace transform on this? Yeah, that's why we switched it to Taylor series, because we know this power functions, we know their transform, right? So let's do Laplace transform on this function, which is going to be Laplace transform of 1 on s minus, let's get the number out, Laplace transform of t squared on s. Let's get the number of multiple out, plus transform of t to the 4th, and so forth, right? So you can see it. So linearity helps, and we can do each one by itself. I keep it on the same page. For one, transform is 1 over s. For this power function and it's a square, it's going to be n factorial divided by s2 plus 1, n plus 1, right? 3, and we have 3 factorial. Then it's actually nice in a way, you just follow the pattern after that. All right, we can simplify a little more. And get 1 over s minus 1 over 3 s cubed plus 1 over 5 s to the 5th minus 1 over 7 s to the 7th plus to the. And here we can verify different things, what we need. And we can also show that this thing converges to the function. We can also show that this, of course, you get here, but with experience of previous calculus, you can also check what it converges to. And here it's going to converge to arctangent. Arctangent 1 over s. So yeah, so here is Laplace transform for sine of t divided by t on s is actually arctangent. So you can add these to your formula sheet. All right, I'll stop here, and another video for some bigger examples, just like maybe the first one I did. Thank you.